category. So here I simply assume the force and the moment in terms of our sign. But you can assume either direction if you like. Okay. So now we're looking for is what is the value of the m and what is the value of the v. And now we simply take the equilibrium equations, the force in y direction equal to 0. So in y direction equal to 0, that means v downward plus 3, this one downward plus the distributed loading, that is 3.5 per length, and multiply the length is 2.4. The whole thing must be equal to 0. And this one is downward. So from, yes?
Do you have to include RA, like the reaction?
Oh, yes, I forgot it. A good catch. I forgot this one. 6.75, yes. And so in this way, I multiply this one plus 6.75 equal to 0. So from here, we can calculate what is V. The V will be equal to minus 1.65.
Is down positive? Are you saying that down is positive or up is positive? Like, does it, or does, are you?
Here, I assume the V is downward. Okay, and then in this sign convention for these formulations,
Okay,
this
yeah.
is positive. Okay, like this. So V is minus 1.65.
So that would actually be minus 6.75 up there.
So here you can see the value is minus 6.5, and here is our sign. So that means exactly is what we show here. At this point, the amount is minus. Got it?
She means on your sum of Fy?
Yeah, so which means here I would say here the V equal to minus 1.65. So that means equivalent to say V is actually upwarding like that.
Yeah.
Okay, so at this section here, at this section V is the acting upward with that magnitude. Per our calculation. Okay, because earlier I assumed, so, got it? Let me do this one more time. So how about this? This time I assume the V is upward. So if I assume the V is upward, let me say the positive upward. Okay? So for this case, V upward, and then 6.5 downward, and then 3 downward, and 6.5 is upward. And then distributed loading, that is downward, 3.5 times 2.4. This one must be equal to 0. So from here we can see V should be equal to how much? 1.65. Okay, so V here equal to 1.65 and upward, and then we pick up our sign convention, so that should be this amount minus here. And now for M, we take the moment equal to 0. And again, for the formulations, we take this as a positive in our formulation of the equilibrium equations. So the first one is M, what we have here. So let me cross out this one. And say, let me take the M about this point equal to 0, okay? So about this point, the left side equal to 0. So we have this one, and then we plus our V multiply with 2.4. The M is in this way, V contribute, the bending is in that way, so positive per our sign here. And then plus this one, N, 2.7, so that is this one, and again that is contribution in this way, so positive.
How are you getting 165?
Yeah, it should be 4.65 because you.
How much?
The V doesn't.
It should be 4.65.
4.65?
Yes. It should be 4.65, and also 3.5, the first one that's not multiplied, should just be 3.
No, 3.5 times 3.4.
Yeah, it should be 3, not 3.5. 3 down.
Oh, how come?
No, okay, so there's the 2.4, which is the distance, the total distance, times the W down, which is 3.5. So that part's correct. And it's minus 3 because it's the force down is 3. And
And then it equals 4.65.
yeah. I,
I think it's a negative.
Oh, yes.
yeah. Well, no, he's
yes.
saying up is
Yeah.
positive, so in this case, that would be correct.
Okay, so I think that is right. And we're looking for is from here to here. Because here because here we select the sections. The section is just over this point where the loading here applied. So that means here we have the discontinuity, and that is providing our value. So here, from here, the value here is minus 4.65. That should be this value here. Are we okay? Okay, now we continue on here. So here is, okay, what we have. So we have M, and we have calculate contribution from V, and then we have calculate the M. The other one we calculate from the 3. So 3 minus times 2.4. Okay, and then the other one. So right now we have 1, 2, 3, 4 being counted. Then the last one is the loading from the distributed loading. Distributed loading we can quickly calculate is this. If you remember in your studies, we can make an equivalent concentrated loading here, and we simply multiply that concentrated loading with the half of the distance, because that's a uniform. So for this case, this is 3.5, this force equal to 3.5 times 2.4. Okay, and that is the equivalent force representing the concentrated loading applied in this range. So that one, the final one is 3.4 times 2.4 squared divided by 2 equal to 0. Okay? Yes?
I just have a question. So you said the distributed load goes halfway in between, so if the overall length's 2.4, should it be at 1.2?
Here is 2.4, yes. So if you want to get it done, we can get it 3.4 times 2.4 times 2.4 divided by 2.
Oh, okay.
The same thing like this. So here V, we calculate, we introduce equal to 4.65. So anyone can punch your calculator how much M will be. I think it should be 3.42. Okay. $3.42 is around here. The value of 3.42 here. And I can provide you the value here at this point here is 6.12. So here we have discontinuity. This discontinuity is about exactly 2.7. 2.7 is the discrepancies at this point, and that is exactly provided by this amount. Okay, so now from here, from this point onward, we continue using the parabolic curve, and now in this range, the slope becomes negative. So here is the negative slope, and eventually it should wind up here. We can check. So this is the drawing of the curve. So those are the parabolic. The same thing here, parabolic. Okay, and here I do the calculation in this portion. Basically, is just want to show you if we have the externally applied bending at this point, that will create the discontinuity here, and that amount will be 2.7. But the matter is whether that discontinuity will be downward or upward, and many times it is not easy to visualize. So the best way is simply use the free body diagram to help us to determine the value. Oh. Okay. So for these questions, if I will ask you where is the maximum bending, then the answer is here. At the position X star, that is at this position here, and how much is the maximum bending, then the value will be this point here, then we can calculate. And I forgot the curve, I erased the curve, but in this way, the maximum bending, let me write up here. The maximum bending occurs at x equal to 1.93 meter from the left, and the value is here I have that one 6.5089. Do you have that equation here? What is the equation for this one?
Oh, that's the negative 1.75x squared plus 6.75x.
Like this one. So basically this value you can calculate it is by this, using that equation, 1.75x plus 6 squared plus 6.5x, and then you simply use the x equal to 1.93 in this calculation. You can obtain this value. Okay, because we already have the description for this curve, so we can calculate the value exactly at whatever we like. Okay. So now, for example, based upon those informations, one step further is this.
Can I ask a question? Mark?
Yes.
Okay, so for backup, if you look at your diagram,
Yes.
so now you have F is equal to 3.4 times 2.4. Where does the 3.4 come from again?
That is the omega, right? Of 3.5. So
okay, that makes more sense.
yeah,
I was like,
that
why
should
is
be
it
3.5.
3.4?
Sorry. Okay, now with those information, we ask you one more step, one question. For example, if the cross section of the problem, for example here, say this is 10 millimeter, this is 60. And that is a cross section. I'm asking where is the maximum tensile bending stress? Where and what is the value? So in this way, we can see right now these are cross sections, and we know that the bending stress is my over I. Okay, this is the magnitude. And for this case, this is a centroid. So the neutral axis will pass the centroid. The neutral axis for this example, two options, either this or this. Which one? Horizontal one. Why? Because the bending for this case, you can see the bending actually is not uniform anymore, but on every single cross section, the bending is to bend the beam like this. Not uniform anymore, not pure bending anymore, because you can see the bending, the value of the bending is changing. But it still has a tendency like this or like this. The positive M meaning bent up, right? So now we're looking for the maximum tension, then we have to look for whatever the maximum bending. So that means the M using the maximum value, and then multiply the Y using the maximum value, and then divide by I. So for this case, the maximum bending is what we have calculated there. So that is 6.5089 kilonewton meter, and multiply with Y. And what is Y? So right now for this case, the bending is all positive. So that bending is positive. So that bending is positive about that. So bending, this is Z-axis. The bending will be working is about the Z-axis in these directions. At any single cross section, the bending will be working like that. Are we okay? Okay, and now we determine, so here in this way, the lower portion will be in tension. So the maximum bending stress, tension will be here. Bending stress, tension. And then the value, Y here we can pick up is 30 millimeter. And then for this case, I we can quickly calculate is 112 and 10 times 60 to the cube millimeter to the fourth power. So we carefully convert the unit, that will be the answer. And this one will be happening right here, right under, for example, let me try here. So let me highlight. So from the front view point, the maximum tensile stress will be here. Okay. So this is regarding the design of the problems. Using this example, actually, we have practiced many things using the equations to help us draw the curve. Once you get familiar with the process, and believe me, you can draw the curve in very short of time. Okay, for practice, my suggestion for you is once you draw the curve piece by piece, on the other side, you work on your free body diagrams one by one to benchmark your drawing. And once you know everything, you know you handle the skills so good, then you can directly draw the things and without the free body diagrams. Again, the purpose we learned the shear and moment diagram is for the design problems like this. Okay, we want to get information about the distribution, for example, the bending. Then use that information, we can know where we calculate and what's the value of that one. That is the purpose, and I think that will be part of your homework for this week. That is due on Sunday. So that is part of the purpose of this homework exercise. Okay, so this is the one, and then there's a more exercise example I posted on Blackboard, and then go over the example.
On our test, are we going to be required to produce